Okay, Professor Wu, can you hear me?
Yes.
Very good. Yes. So please start. You have to present around the 10 minutes. Thank you very much.
Hello again to Mustafa and Professor Wu. I start my presentation. My
Okay,
name
go
is
ahead.
Begini. I've recently graduated from Iran University of Science, IUSD. My under the supervision of Professor Majid Rajabi, and my thesis was based on quasi-restiveness rotational dampers for isolation of torsional systems. My main research focus was on nonlinear dynamics, linear and nonlinear vibrational isolation, and vibrational and acoustical characteristics of metamaterials. Uh, I have skills in both simulation and CAD modeling. For example, I've worked with SolidWorks and with Abacus for my simulation. And concurrently, I work with COMSOL for acoustical research. My industry experience was about designing beams and optimizing beams for solar tracks and solar panels. My main work was on designing the best configuration of beams and arrays for maximum beneficiality. And also I conduct a little research about design for manufacturing and design for assembly for the company that I joined, I think, 4 months ago. My two references are Professor Talebi and Rajabi. Mr. Rajabi was my supervisor uh, during my bachelor degree. Currently, I work with Professor Talebi and his team. The main focus are on both acoustics and vibration. Uh, they team and they team cover majority of topics and research. Uh, my publication are about have two terms. One of them are quasi-restiveness torsional vibration isolator under the supervision of Professor Rajabi. Another my publication was about muffler, and it has acoustical themes, and it was under supervision of Dr. Talibi, as I explained it in more detail in next slides. And also, I've joined Professor Talibi's team, I think a year ago, and I conduct research in that team. My main theme was modeling TPMS structure and simulate uh, vibrational and acoustical characteristic of TPMS panels and structures. Also, I study a little bit solid characteristic of TPMS and the hybridization of TPMS unit cells and their improvement on their mechanical characteristics. This is the historical statistics of my main research that is quasi-restiveness. It is obvious from the figure that it gained very attraction during last decade. The number of publication and citation grown recently year by year. Uh, my uh, my main focus on my research on quasi-recipients torsional isolation is my main configuration system is something like this. Is kind of coupling. If you see precisely, you can see number 7 and number as an uh, elastic that provide you torsional stiffness, and with combining with the stiffness of spring, that is number 6, you can have quasi stiffness uh, isolator, which means you have around quasi stiffness of 0 around the equilibrium point. That means you can lower the natural frequency of the system and have isolation under lower frequency. This is the configuration of my system, the notation I've used in my research, and by calculating the moment of the spring that has around the central axis and combining with the torsional stiffness of the elastic, you can uh, adjust the stiffness of the whole system. And if you adjust the stiffness of the whole system around 0, you can reach quasi-stiffness characteristic. My main goal was using hardening and softening spring because of the improvement that we can by using these instead of linear spring. Um, During my research, we saw that by implementing hardening and softening effects for spring, we can have better results. I show them later. This is my formula for conducting my research, and the main feature of quasi-recipientist systems are their stiffness should be 0 around the equilibrium point, and the stiffness can be obtained from the derivative of the momentum around the central axis, and the moment of this nonlinear system can be obtained from combining both effect of torsional stiffness of the plastic, and also by manipulating the force times the distance of the uh, spring force around the central axis. Well, this is my validation that I was validating my work with Zhu et al. And they work on linear system, but I improved the system. And as it is obvious from this figure, if you soften the spring, you can have broader range of quasi-recipientist characteristic, as it obvious from figure A above. And it is worth mentioning that if you make your system very softened, you cannot have a stable system, and your system become unstable. So it is important to note that your system must not uh, soften too much degree that their stiffness, their stability reduce, and it doesn't have reduce. If you increase the softening feature of uh, the spring, you can improve the quasi-recipient's characteristics a little bit, but you should don't you should not you must not use a very softened spring. Another work that I conducted, and I said it earlier, was about designing muffler, as it obvious from the figure left above, and the acoustical characteristic of this muffler. We use TPMS materials as an structure that help us uh, increase increase the degree that the system can absorb attenuate sound. And as it obvious from the figures, we clarified that if you use uh, regarding simple mufflers, you cannot reach transmission loss very much. Yeah, and when we use TPMS structure as a structure that help us to attenuate sound, the degree to which this system absorb the sounds, it's obvious, and it is much higher than typical systems and mufflers. And as it in the left of the page, we can see our experimental test that we conducted. We connect our muffler. to the impedance tube, and by adjusting the frequency, I think to uh, 3000 hertz, we compare the result with our numerical results, and it is obvious from the figure, right? And we as it is worth to mention, we have agreement with uh, numerical results, and that is ensure that our numerical results was correct and conducted precisely. My future plan for research is based on my recent researches, and I want to explore more about the nonlinear effects of quasi-restiveness, and I want to I would be happy to use them as an devices in many spectra. For example, you can use them in a marine application, you can use them in aerospace application, you can use them in everywhere you have a harsh environment and you want to isolate uh, two systems from another. For example, in the context of uh, sensors, and you can use materials or any configuration that provide you quasi-recipient's characteristic to to prevent noise from harsh environment, and or everywhere you have torsional disturbance, you can use these systems quasi-restiveness as an device to help you increase the durability of your system, increase the healthiness of your system, or prevent the fatigue from your systems. And also, I want to explore the control side of this structure by using pneumatic or magnetic device instead of uh, simple spring. You can have controllability over this structure, and you can make this structure adjustable to their environment. You can adjust the stiffness and also the damping effect of this device, and boosting their possibility to isolate every vibration in every uh, environment. Uh, Also, we can say that my work was something like a mechanism of quasi-recipients. You can provide quasi-recipients characteristic by using negative stiffness plus positive stiffness, and these stiffness can be provided with, for example, origami structures that are which are structures that if you they are foldable, and if you fold it there, if you have them folded, you can have you can provide something like quasi-resistant characteristic that is obvious from this figure. Also, uh, all of the dynamical system can be stochastic. If I can, we can consider the random vibration and also stochastic loading on this configuration, because it is obvious we have rolling wall on this uh, profile of that is obvious from the picture below, and if your force is higher than the degree, you have not your ball contact with the circular profile, and this means that for sometimes you have not contact of balls to this system, and your system becomes stochastic. Also, we can consider the effect of the effect of different spring configuration. For example, bilinear stiffness or saturation or clearance spring for this device, and see if they boost the quasi-recipient's characteristic or device or not. And also, I want I recently mentor a group that work on origami of mufflers, which means that the muffler was designed by implementing origami orifice that can help you by adjusting the angle of the duct. You can have adjustable uh, and selective frequency isolation by using that origami configuration. And yes, another research theme that I enjoy to work on is considering the characteristic of uh, acoustic of metamaterials. That is very interesting for me, and I think it absorbs a lot attention of researchers and scientists. I'm done, and that is my end of my presentation. If there is any question, I would happy to answer those questions.
Thank you very much, Soil. Yes, Professor Wu.
Yeah. So, how to pronounce your name?
Yes, Soil, please pronounce your name.
Suheile Chegini.
So hey,
But yes, yes.
Yes, the
so
first name
hey,
is Sohail.
yeah.
Yes.
So hey, so where are you now? So I saw your
I'm
CV. You are graduate from Chongqing University.
Yes, I'm recently graduated from Iran University of Science and Technology.
Yeah, you are undergraduate students, right?
Yes, yes,
Uh,
undergraduated. Yes.
Yeah.
yes, yes,
Yeah.
I graduated from bachelor degree. Yes.
Bachelor degree. So where are you now?
Um, I'm from Iran. If you mean where is my country?
Oh, you're still living in Iran right
Ye-
now, right?
Yes, yes.
So uh, how about your cooperation with? I think in your CV you have you did not. Okay, so the two professors are also from Iran University, right?
Yes, yes. Professor Majid Rajavi and Professor Rolo Talebi. Yes.
Let me see. Let me see. Okay, let's go back to your research about the isolator.
Mm-hmm.
Go back to your slides. So you are mainly focused on vibration uh,
Yes, yes. My
research.
focus was on torsional isolation. Also, the system can be used in linear isolation.
Yeah,
More possible to use, and also they are both can be adjustable and use different mechanism for providing the quasi recipients of this
yeah.
structure.
So go to slides. I think go to slide 10, 12.
Well, okay.
The 13, 13, slide 13. So you have done the research about the T 13, 13. Next
Yes,
one.
setting,
Yes.
setting, experimental.
Uh-huh.
Not experiment, it's muffler design. You have also done this kind of research. So
Yes.
it's about experimental validation, or you
Yes.
design this one.
I conducted numerical and experimental research on the absorption characteristic of TPMS metamaterials.
Yeah. So what's the highlights of this kind of design? TPMS. So do you
Okay.
understand my question?
Can you repeat your question? I can understand it.
Yeah. So what's the innovation of
Uh-huh.
this?
Okay, I got that. TPMS structure have not yet used for a muffler. The main characteristic that the researcher and scientists explore and investigate their acoustical characteristic, but they have not yet been used in the context of the muffler, and they have not research on the STL or sound transmission of this structure and compare this structure with together. The only term that has been, I think, conducted is only there was simple panel of this PMS or double curve of this structure, and they only considered the normal and radial sound dissipation across this structure. I think this structure can can be considered as an, I think, Helmholtz, because the porosity this structure has help the system to attenuate and absorb the sound. And as it obvious, it from the figure below, the green line is a typical muffler with equal mass of this structure, and the blue line is P-type TPMS, that is means primitive TPMS conical muffler. And as you see that, the degree to which the system attenuate the sound is much higher than the typical muffler.
Okay, so so what's your contribution in this work?
In this work, I designed this muffler in a topology, and for the first time, it is very hard to model this structure. And also, I meshed it in hypermesh and helped my a friend of helped my friend to simulate this muffler in console. Let's briefly say what I do.
Mm-hmm.
I designed the CAD model of this system, and also I mesh it in hypermesh and give the meshed structure to my friend to conduct the acoustical simulation. Also, beside that, I search for to how to print this structure, because this structure have porosity. It is very hard to extract a G code for printing this structure, and I think it takes I think 2 weeks to slice and extracting the G code of this structure to have this structure printed for experimental test. All of the experimental tests and the printing process was on myself, and I do them correctly. And as it always, the numerical results and experimental results have good agreement.
Mm-hmm. So as you said, the numerical and experimental result has agree with each other very well. So have you done the numerical simulation on the acoustic performance?
Yes, I worked recently. I worked with a colleague, with a postdoc, with he works on double curve and the acoustic characteristics of double curve. Yes, I work a little bit and with COMSOL and conduct a research about their characteristics. We work with acoustical module of COMSOL for this simulation.
So can you tell me in detail what kind of module in console for acoustic simulation?
One of the key points that we consider in this we don't
Uh,
consider in this uh, research, which was harmonic acoustic, and the advisor of the journal said that you should consider the characteristic of phalloid, and you have heat dissipation, and also you have shear characteristics. You don't consider the uh, shear characteristic of phalloid on this structure. And yes, I only work with simple acoustic module of the console. And yes, I would enjoy to work more precisely and consider thermoacoustics of the domain that the sound wave are propagated.
Yeah. So the CAD and the mesh, you have very familiar with these two kind of softwares.
Yes, yes. CAD modeling and exporting image and a little bit work with console in the simple acoustic module, which is
No,
a harmonic acoustic, I think.
yes. That means you have good skills in software using. How about your programming skill?
Yes. For extracting my research on quasi-recipients, I spent plenty of time coding with MATLAB, and also I won a competition in Python when I was in the third semester. Yes, I have a familiarity with Python, and yes, I work in plenty of time with MATLAB.
So how about your uh, I mean, Python and MATLAB are popular in universities. How about the programming skills with C++?
C++. Also, in the third semester, uh, uh, we should learn something about C++. I have only familiarity with C++, but if I have time, for example, 1 month or 2 months, I can get very retain my knowledge, and I can be familiar and work with C++. Because I learn Python and MATLAB, I think and also I learn a little bit C++. It means that I can learn it very fast in C++ and use them as a code to conduct researches in every domain we want.
Okay. So do you know, have you done some research on our group? Uh, what we are, what we have, what are our research fields of my
Uh,
research?
our university, my university,
No, you want to apply the
yes, I
uh,
want to apply for university, yes.
for you want to apply STTO. So I think you want to join in our group. So
Yes.
which kind of research would you like to do in the future if you join in us?
I also I enjoy both acoustics and vibration. As I mentioned, I can work on isolation. I've not yet worked on conditional monitoring. It is enjoyable for me for work on that. Yes, I can work on both acoustics domains and expertise, and also on vibrational areas of research and something like that.
Okay. So can you go to your research plan next?
This slide you mean?
No, no, previous.
Previous. Please?
Yeah, this is isolation, right?
Yes, this is a different configuration of torsional isolation. Two figures below show that a marine application of quasi-recipients. You have propeller and motor. If you have harsh environment around the propeller, for example, because of the bad situation of the fluid or something like that, you don't want to this vibration go to motor and disappear, and you want to disappear in the middle domain. And as it is obvious by designing a torsional quasi-recipients
Yeah, okay.
isolator, you can achieve this harsh environment, harsh effect
So,
of environment.
so but it's a little bit different from our research. So go to next.
This kind of research is considering the control characteristic for spring and dampers. And you can use a magnetic device or pneumatic spring
Okay.
as a tool for.
Hmm. So I got it. So any other slides you want? Is the end of your slide?
Yes, that is the end of my slide.
Yeah. So slide 15. 15.
Uh-huh. Okay,
Uh-huh.
this is the domains that we can use a quasi-recipient's device to attenuate the vibration. It is said that under the sinusoidal excitation or bump excitation, they show the good vibrational characteristic, and you can have lower frequency isolation for the lower frequency excitation.
Mm-hmm. So my research is mainly focused on acoustic problems.
Mhm.
Hmm. So I think Hasanu, did you
Yes.
tell him what we have done here?
Yeah, yeah, yeah.
Yeah. So something like numerical methods for acoustic simulations.
Yes, yes. Currently, I work on acoustic characteristic of the origami mufflers. I am familiar with our acoustics. I'm not yet familiar with the theory of acoustic, and I enjoy spending time that learn and deeply too much on the theory of
Yeah.
the acoustics. But I've got familiar with the research I conducted in
Mhm.
considering the acoustic characteristic of double curve sandwich panels. And with my colleague, we postdoc students that use, I think, third shift theory to model the acoustic characteristic of double curve. They first
Mhm.
extract the mode shape and the vibrational characteristic of that double curve structure, and by using those formulation and considering the vibration characteristic, they uh, derive the acoustical response on the radial excitation of acoustic waves.
Mhm. So one question. So you should tell me what kind of research you want to do if you join.
Uh, I would enjoy work on the acoustic characteristic of mufflers and dogs. Also by uh, co- uh, sound absorption is one of the main things I enjoy spending time on. Or driving and go deeply on the theories of the acoustic, or for example, marine acoustic or something like that. Or also we can work on the conditional monitoring and phase array or something like that that consider the system's response under acoustic excitation to explore their durability and healthiness.
Mhm. So so let me clarify it. So how to use the screen? I don't how to make marks on the screen. Asano.
Yeah. What should I do?
How to write? I mean how to how to make notes on the screen.
Make a note.
Yeah, I want
Uh,
I want to write something on screen.
Yeah, I think with this chat. Yeah, you can use with
Which one?
chat. Yes. On the screen, please see the screen. Show conversation. Yes, yeah. You can write everything here.
Well, so I can something on wrong typing. I don't think so. I can use this
On the screen, you can see chat beside the people.
chat. 稍等一会儿啊。where
Up to up to
Capgemini
up to your screen. HW.
on my screen.
Yes, up to your screen chat.
My screen is here. You can see that beside people, you can use chat. Do you have my screen share? I have my screen share.
Yeah, let me see because I'm not very familiar with this software.
Yes, this chat is there. You can see my cursor, mouse cursor.